The scientific method, as we continue our notes, it's a pattern that is loosely followed in the scientific community. It's a good guideline. It's a good starting point, a good structure for looking at a problem and trying to figure out how you can find a solution. You don't have to start at a certain part of this scientific method in order for your scientific exploration to be valid or anything. But the general part, the overall sort of structure of how we do science or how you attack a science problem is this. You observe something. Usually there's some kind of observation, and it either makes you question something, or you notice an irregularity and you wonder why that is, or you make some sort of observations about a problem that you're encountering. Hypothesis. This is just a fancy word for making a guess, an educated sort of informed guess. Maybe you don't know a lot about the subject and maybe your guess is pretty wild, but let's say you notice that there are a lot of students coming late to school, okay, and that's an observation. You have some ideas about why that might be. You might think, well, traffic is heavy, or they really don't know what time school starts, or, the Tim Hortons line is always really long and they just can't figure out they need to leave 10 minutes earlier. You may have your ideas as to why something is happening. So what you would do then is you would actually start to test your hypothesis. So you might ask questions of the people that are late. Let's say you're trying to get to the bottom of why so many people are late for first period at school. And you ask them, you say, so I noticed you were late today. They might say, get lost, but you might say, I'm just doing a scientific experiment here. I'm just trying to explore the scientific method. And you say, can you tell me, did you go to Tim Hortons this morning? And they say, no. Okay. Was traffic really heavy this morning? Yeah, actually, I stood at, we sat at that light for a lot longer than normal. I don't know why. Okay, well, was there construction? Actually, yeah, I did see a construction sign, and actually, now that I think about it, there was a lane closed off, and yeah, we all had to kind of go into the one lane. So, okay, well, now you can falsify the idea of Tim Hortons. Okay, they didn't go to Tim Hortons, or they know what time class starts. Do you know what I mean? You can start stroking that stuff off the list. Okay. And so you start to write down these answers to these questions, okay? And so you kind of get to this point where, okay, I had a hypothesis here that people are late because they didn't know what time school started. You asked them, they said they do know. All the people that were late actually do know the class starts at 8:45. And so you're saying, okay, I guess I got to change what I think about that. Maybe it's the Tim Hortons hypothesis. Let's ask them about Tim Hortons. So in our questioning, we're kind of following this, okay? They didn't go to Tim Hortons. That's the result. Okay, so let's go back and change my hypothesis. Traffic. Okay, let's ask about traffic. Well, yes, actually, they did sit at the light for longer than usual. Why was that? So this evidence supports the hypothesis. You can go back. Okay, well, let's talk again. Why was that? Did you see any construction, or was there snow, or whatever? And then you can basically come up with your theory as to why these students were late. And your conclusion would be, you know what, there was construction, they had to sit longer at a light. Why was that? Traffic was congested because it was down to one lane on the way to school. There you go. You have a solution to the problem. Okay? Now, like I say, you don't have to, every time you want to find the answer to a problem, you don't have to look at this and say, okay, check, here I'm at this box, and now I got to follow this arrow. And we do this sort of automatically. But it's good for us to actually recognize sort of the structure of our of our questioning. And so that's something that, we call the scientific method. You notice something, you have an idea, you test that idea. If your idea was wrong, you go back and you have another idea, test that one. If it's wrong, go back. If it's right, okay, well, there you go. Now you can make some kind of conclusion, you can make some kind of assessment, or you can make some kind of statement about a solution to a problem. Okay, measurement. Let's talk about measurement. In Physical Science 20, a big part of the first section is talking about numbers and measurement and the precision of numbers and so on and so forth. So in math, numbers are often called figures. Okay? In science, we want our work to be as exact as possible. So what being exact means is that we want to use the best and most exact measurement possible. So the one that's the most, it's the most precise, really. The most exact measurement includes only significant figures. So we're going to talk a little bit about significant figures a little bit more later. How many of you have heard of significant figures before? Okay, maybe in your grade 10 science. Did you talk about sig figs or significant figures in science before? Yeah, some of you are nodding, some of you are shaking, some of you are just trembling. Okay. Okay, that's fine. We'll talk about more about sig figs a little bit later. So let me talk a little bit about this. Now you don't have to copy this whole thing down. You can if you want. I'm going to be on this slide for a few minutes. But here's the thing. Whenever we take a measurement, there's a certain measure of uncertainty about the measurement. Okay? So whenever we take a measurement, and I didn't underline this page, I guess, for you, there's a certain measure of uncertainty about the measurement. So let me just stop and explain that real quick. If I say, that I'm, okay, actually, I'm going to ask you guys, how old do you think I am? Go ahead. If I say that I am 42 years old, and thanks for all guessing under that, appreciate that. If I'm 42, there's a certain amount of uncertainty about that number, isn't there? Because you're thinking, okay, he's 42, but you are understanding that it could be my birthday today and I'm exactly 42. Like maybe I was born at 10:14 in the morning on this day 42 years ago. Boom, I would be exactly 42.000 years old, right? But if I just say I'm 42, or let's say you guys are what, 15? Oh, 16. We got some 16s in the crowd. All right, good job. So let's talk about you guys now. Let's say you're 16. Okay, well, is it your birthday today? Are you exactly 16? Like, were you born a few hours ago, 16 years ago? Or are you 16 and a half? Are you 16 and 3 months and 3 days? Do you see how there's some uncertainty? Okay? With every number and with every measurement, there is some uncertainty. No matter how exact you get, there's always a little bit of uncertainty. And so let's look at this ruler here, okay? So if this ruler, okay, didn't have these little notches, let's say we just look at the top half of this ruler, and it's in solid, let's say this is centimeters, or actually, let's say 1, 2, 3, 4, 5, okay, centimeters. And let's say that you have this metal strip and you're measuring this. Well, you would only be able to say, hey, you know what, this is pretty close to 5 centimeters, but I know it's a little bit more, so I'm going to guess it's about 5.2. And that's as much as you could go. You couldn't say 5.275993. You can't do that because you're just making up numbers. Because what you see right here is it is definitely a little bit longer than 5. And so the uncertainty is you can go to one more digit or one more figure and you can say, I'm guessing with confidence that this is 5.2 centimeters. But that last figure, that last digit, is always a little uncertain. Let's contrast this with the bottom part of the ruler. Okay, now the bottom part of the ruler it's a little bit more precise, isn't it? Because it's actually marked out for you the tenths. Okay, now look at the same metal strip with this ruler down here. You can say, okay, I know it's more than 5, but look if you look really close, you can say, I know that it's even more than 5.1. But it's not 5.2. See that? It's not quite, it's between 5.1 and 5.2. And so you can actually say, I think this is 5.1. That I am confident of. The next number, though, is my guess. And the last number is always uncertain. You can do that when you're measuring something. So you would say this one, 5.15, because this looks like exactly in between. Although we're not quite sure, are we? So 5.15. So I've summarized that in the notes below here, okay? All right? So jot down whatever you wish, make your jot notes or whatever. But it's easy to see that the measurement on the bottom is more exact, isn't it? Because there's more precise gradations on the ruler, right? There's more marks on the ruler. So the measurement on the top is 5 point something, and we guessed 5.2, didn't we? Or I did. And the measurement of the bottom, though, we know is 5.1 something. And so we could go to 5.1, I think we said 5.15. So it depends on the measuring tool how precise your measurement can be. In the bottom measurement, we knew for sure that the metal strip was 5.1 centimeters long, but we also knew that it was some amount longer than that. So this important information, if you want the measurement to be as accurate as possible, you need to kind of use that information and say, hey, you know what, I got to tell you that it's more than 5.1, okay? Significant figures. Okay, these are called sig figs. You'll hear me call them sig figs. You can call them sig figs if you want. If we're doing an assignment and you do not have the proper number of sig figs in your measurement or in your answer, you'll see me write SF apostrophe S. And that just means, hey, you know what, you don't have the right number of significant figures in your answer. But sig figs are something that I normally call them. So, whenever we give a measurement in science, we should always give all of the digits that we are certain of, plus the first estimate. So this is, excuse me, still early on in the school year, my voice isn't quite 100% strong yet. When we give a measurement in science, we want to report all of the digits that are certain, plus the first estimate. So that's what I was talking about. All of the ones that are certain on that measurement on that ruler, plus one more. And we can guess one more. And that's okay. All of these digits are called significant digits or significant figures, because they speak to the precision of the measurement. And they're all of the important numbers that are considered. And so significant figures, the more significant figures you have in a measurement, the more precise it is. And I'm not sure if I have that in my notes anywhere else, but that is something that needs to be written down here. I think, yeah, it's down. It's later. I don't want to spoil it for you, so I won't write it down here. But anyways, now, when we're doing measurements, or when you see a measurement, okay, you need to be able to recognize how many significant figures there are in that measurement. And if all of the numbers are not 0, if they're all between 1 and 9, all the numbers or all the digits in a number, then that's easy. They're all significant. But here's some rules on how to determine which figures or which digits in a number are significant. Okay? So, for example, this one was easy. There's 3 significant figures because they're all non-zero digits. Here, there's just 2 significant figures. Everyone see that? So the first rule, you might want to write down, here is this. So, rules for sig figs, if you're titling this. Rules for sig figs. In a measurement, number 1 says that all non-zero digits are significant. And it would probably be good for you, I mean, if you want, you can write down the numbers 1 to 9, it doesn't matter to me. But if you see a measurement, and all of the digits in that measurement are between 1 and 9, then they're all significant. You count them all. That's rule number 1. Rule number 2, and the rest of the rules really talk about the zeros, because that's where it gets kind of iffy. Like, are the zeros counted as being significant or not? So rule number 2 says all zeros between non-zero digits are significant.